Hi everyone, Mr. Boltry here bringing you video 4.4. We're going to talk about collisions in the two dimensions. So first we're going to review the idea of applying conservation of momentum to collisions, and then we're going to do an example where there is an object that is colliding in two dimensions. So first, the idea of conservation of momentum. We've said that if there is no impulse, then there's going to be no change in momentum. And the easiest examples where there's no impulse are in something like a collision or a explosion where all of the forces are internal to our system. And that relies being on a frictionless surface, which is usually a pretty basic assumption that we make in our collisions examples. Or the other thing that I kind of didn't really talk about a lot in class is sometimes even if it's like cars colliding, we can say the conservation of momentum basically applies because while there is some friction and other forces acting during the collision, the force of the collision itself is so much bigger than those other forces that we can basically pretend like they don't exist. So for the purposes of AP, during collisions and explosions, we say that momentum is conserved. Whether it absolutely 100% is or not is then we can calculate a percent error based on that. So if there's no external force, then that means the change momentum is zero, which means the final momentum minus the initial momentum equals zero, which means that these two things are equal to each other in magnitude. So that means however much momentum we have at the beginning is going to equal however much momentum we have at the end. That's just the most important thing for these to be zero. So in 2D, we're going to apply the same rule, except we're going to look at it in the x direction and the y direction separately. So in the horizontal direction, there's going to be no change in momentum. In the vertical direction, there's going to be no change in momentum. So the way that I like to structure these problems is we're looking kind of at four different boxes. We're looking at the initial momentum and the final momentum in the x direction and the y direction. So to sort of segment everything, I like to make this grid that has initial, final, x and y just to keep everything in its proper place. So to show you an example of how to use this table, we're going to do a practice problem, which I've pulled from the Khan Academy's website. So billiards is an example that the AP loves just because we have this nice, smooth, near frictionless pool table. And then the collisions, they make nice big clacking sounds and it works pretty well. So we have a stationary stationary yellow ball. And then we hit this white ball towards the yellow ball. And we're given information about the masses of the billiard balls and how long it takes for this white ball to travel 1 meter and this yellow ball to travel 1 meter. And then from that, we can ask a series of questions. But the question that I'd like to answer today is, what is the velocity of the white ball after it hits the yellow ball and sort of flies off in a random direction? Because we know how fast the yellow ball goes because it only takes 0.35 seconds to go this 1 meter. So then how fast is the white ball going? So I'm going to set up my table, and in each of these boxes, I'm going to have a momentum for the white ball and a momentum for the yellow ball. So white ball, yellow ball in all four of the boxes. So really, we're solving for 2, 4, 6, 8 momenta, and that will allow us to solve the problem. So looking back at the problem, it's always nice to establish an initial state. I'm going to say the initial state is right before the collision as the white ball is just about to hit the stationary yellow ball. So stationary yellow ball, I know the yellow ball has 0 momentum in both the x and the y direction. The white ball is not moving up or down, it's just moving straight horizontal. So it has 0 momentum in the y direction also. And then we can calculate its momentum by figuring out the velocity, which is how 1 meter divided by 0.25 seconds, meters per second, and then times the mass. And I think I might be covering this up, but the units on all of these, I would put it in there, but then it would have made my table super crowded. But remember, the units for momentum is kilograms times meters per second, which unfortunately doesn't have a fancy name. So anyway, so we have our initial condition, our initial momenta really clearly defined. So then at the end, in the y direction, we should have 0 momentum because these two added together is 0. So no change in momentum, beginning is 0, end is 0. Same thing up here, beginning is 0.72. The end needs to be 0.72 in total. So now let's look at the end scenario and see what information we have. Well, the only thing that we know is the yellow ball goes down and to the right at an angle of 28 degrees, and it takes 0.35 seconds to do that. So we incorporate the 1 meter in 0.35 seconds. We can find the speed of the ball, but we want the x and y components of that speed. So then we're just going to do some sine and cosine with our 28 degrees. We're going to get the x and y components of the speed. Then to get to the momentum, which is what we need because we're using the conservation of momentum, we're going to need to multiply this by the mass of the ball to get mass times velocity. And then we're going to get the horizontal and vertical component of the momentum. Very importantly, make sure you keep this negative sign, which I didn't have. This should be negative 1.34 meters per second because it's going down, and we've established that sort of the top of the table is positive and the bottom of the table is negative. So negative 0.20 kilograms times meters per second. And so then we can find out the final momentum of the white ball in both the x and y direction. So in the x direction, we need a 0.38 plus this number to add up to 0.72, so that the final momentum equals the initial momentum. Same thing down here, we need this and this to add up to be 0. So if you do the math on that, you should get 0.34 kilograms times meters per second and positive 0.20 kilograms times meters per second. And with this, we are so close to being able to find the final velocity of the ball. We just need to recognize that this is our x component, this is our y component, and we want to know the resultant force. So we're going to, first of all, divide by the mass to get the velocity. The x and y components of the velocity, because this is the momentum, kilograms times meter per second. So if we divide by the mass, we get the velocity. Then we're going to use a little bit of Pythagorean theorem to get the final speed of the white ball. So now it depends on if the question asks for the speed or the velocity. If it asks for the velocity, we could either give the vector notation of the velocity, or probably if it's a multiple choice question, it's going to have a degrees. So we need to calculate the angle between these. Then we can just do a little bit of inverse tan to get at an angle of 31 degrees. Which, if we go back to the example, is actually pretty bad for the pool player because it means that their white ball is heading straight for the other corner pocket, which is a scratch, which is no good in pool. But things that are good is the way that we solve this problem using conservation of momentum. We are going to do more practice problems doing conservation of momentum with collisions, especially collisions in 2 dimensions in our next class. Please let me know if you have any questions, but this is Mr. Boltry wrapping up video 4.4, and go Bears.